Okay, nucleophilic aromatic substitution. Recall that we have, in this chapter, been talking mostly about nucleophilic, electrophilic aromatic substitution. Right? But now we're talking about nucleophilic, big difference. So, what we're going to expect now from nucleophilic anything is going to have some kind of a nucleophile, right? Which a really great nucleophile is hydroxide. Nucleophile attacking, oh, I don't know, looking for an electrophile, right? Looking for something like that. Well, it turns out that we're going to get nucleophilic. Whoa, right there? Really? Wait a second. Didn't we just find out that we've got a pi system here? Pi system, which is very, a high density of electrons, right? Didn't we just find that out? So if we have a high density of electrons, we're not expecting a nucleophile to have any attraction to an aromatic ring. Aha! What is this? An electron withdrawer? What? Oh, yes. Okay. All right, let's talk about this. So, can you hear my Keurig going on behind me? Sorry about the noise there. Aromatic rings are generally electron rich. Yes, yes, we know that. Yes, yes, we know. Which allows them to attack electrophiles. Aha. Now, to facilitate attack by a nucleophile. What? By a nucleophile, a ring must be electron poor. Yes, yes. Why? Why must a ring be electron poor? A ring must be substituted with a strong electron withdrawing group. Can you think of any strong electron withdrawers? Page 899, table 19.1. Right? Go look there if you can't think of any. And okay, so stipulation number 1, there has to be electron withdrawing group on it. And stipulation number 2, there has to be a good leaving group. Do you know any good leaving groups? Yes, yes you do. Okay, and then finally the leaving group must be positioned ortho or para to the withdrawing group. Okay? Why? Well, man, I wish I could somehow give you the motivation and the pressure to think about this on your own with a blank sheet of paper and a pencil and your own structures, because you could do it, right? So really, I think the previous slide is all you need to know, and everything else is things you could guess. But let's talk about what you would guess if you had the spirit and the energy to do it. All right, so first of all, we're going to get attack here. Well, you knew that because you memorized it, right? You're going to get attack right there. But here's the reason why. Let me go to a different color. You're going to get attack here, right? Because you have, look at that. You have a polar bond there, right? So everything else is not that, okay? So that's going to be a place where you get your attack, your nucleophilic attack. You recognize this nucleophile. You've seen it, oh, I don't know, maybe 100 times, maybe 1,000 times, right? There's your nucleophile, comes in, attacks right there. Now, when that happens, of course, these electrons got to go somewhere, and that's where they go, right there, wham. And it makes a carb anion. Don't forget your formal charge there. It's important to, there's no reason to drive without guardrails, right? And that's what that is. So in the first step, you have a nucleophile come in right there, push these electrons off to make a carb anion. Now, the Mesenheimer complex is like the sigma complex. Okay? So what you need to do is you need to draw the other resonance structures, okay? Well, I said that right here, didn't I? Draw all resonance contributors to the intermediate. So stop the video right now and do that. Draw those. Okay, so the other resonance structures, I didn't show the other ones. Let me go back. The other resonance structures, you can see those go there. So that's going to make right? And a minus. And I'm going to put the NOO. So minus here and a plus here. Can you see what's going on here? Chloride OH, chlorine OH, okay? Now these, they can go here and they go on to the next page. That structure goes on to the next page. Or they can go here, which goes right here. And if those go there, these electrons go here. Right? You see what's going on here? Electron dots with this pen is a little difficult to make, but that's got a plus on it. This has a minus on it. Okay, I've got all this there. All right, so let's move on now. You still have the other structure, which I have not shown you. It's on the next page. So, and there it is, right? You see the nitrogen's got a lone pair of electrons here. Okay, and then after it resonates, you know, out of the ring into the electron withdrawer, then back into the ring, back into the ring, back up there, boom. Leaving group, gone. Okay. All right, I think this is something, you know, it's definitely within range of what you've learned before. Hopefully some of you are so comfortable with this you're able to predict that. All right. Good. Now, how would the stability of the transition state and the intermediate differ for the following molecule? So draw out all of these. And I don't even think I've got this next slide. Give me a second here. Let me look. Yeah, I don't have these on the next slide. So draw all the intermediate. Draw all the resonance contributors to the Meisenheimer complex. Okay? And then make some statement about the energies. That is, say something about the transition state and the intermediate and how do they differ from the one described before. And that will explain why there's no reaction. And that would be, I think, a hard question. Well, not hard. It would be elaborate. Right, that would require you to make connections in your head before you get to class for the first time. But that would be a good quiz question. Explain why this has to go. Let me write that out so you can see it. Explain why this has to go. Explain why NAS reactions go para or ortho. Wow, explain it. And in doing so, you need to draw all structures of the Meisenheimer complex and say something about their energies. Yep, good question. Okay. Finally, excess hydroxide is used to drive the reaction forward because it deprotonates the it's the excess hydroxide that is used as the nucleophile. It deprotonates the phenol, right? So you've got this hydroxide, but you've got a bunch of it, right? And you know phenol is a better acid than water, so it's going to deprotonate, right? So in other words, you really have to add acid at the end here. So the name of the game is, number one, doing all that. Number two, adding acid, and when you do, you get your substitution product. Wow. Hope you like it. Pretty cool.